We'll proceed in calculation of curl, fundamental of curl in calculus. What is curl and what is curl and how it makes sense in calculus, how it is useful, so that we will see. So we are seeing it for past few kind of videos episode. We are seeing curl in calculus. So we know vector field. So vector field is a vector which components are not numeric rather than it is algebraic. That is vector field. So if I have a vector field called xi, if I have a vector field called xi, if this is x-axis and this is vector field xi. So xi in I direction. So this is the vector field. Now what is curling? If this is the vector field, if I place an item in the vector field, what is the tendency of the vector field to rotate the item? That is called tendency of a vector field of rotation. If vector field carry tendency of rotation, then we say that vector field has curl component. It is has curl field. This is curling. Curling means rotating something. If I have a vector field that is xi, this is x-axis xi, and if I place something and it rotates it, then xi vector field has rotation tendency. How much this tendency is? That is curl component, curl magnitude that we would calculate. So that is the kind of concept. How much it is that we would calculate. Simple. So if it is xi, then certainly it will not rotate. If it is xi, then probably it would not rotate. But if it is something different, it may rotate. How I can find that a vector field would rotate an item or it would not rotate an item? So to find that, we land up in proving that our vector field is path independent or not somehow. To know a vector field has tendency to rotate something or not, for that we came to an area where we are trying to find the vector field is path independent or not. Path independent in the sense that if I have a vector field, this is x-axis. So if I have a vector field, this is vector field, and I have a path, this is a circular path and vector. Consider vector field as magnetic field. So full magnetic field is passing like this. If I calculate magnetic force. So if I say force into displacement, that is work done. If I place a kind of a iron here, in a way, okay, so that there is a repelling magnetic force repel, or if it attracts, then magnetic force is from this direction to this direction. If I place an iron here and iron moves like this to this side, so this is considered as magnetic field did the work, magnetic force did the work. If that is the case, then this is point A, and from point A to it move to point B, because magnetic field is in this direction. So iron got attracted and it moved from this direction toward the magnet. So this much work done. So work done is from point A to point B. Okay. Now if I take a straight line where point A and point B are same, but connecting point is a straight line. Earlier it was a circle. If this is the magnetic field, then how much is the work done from point A to point B? That is magnetic force into distance. So this is the distance. Earlier, this was the distance. If this is circular, if this is circular region, point A and point B, then this was the distance. So if the force into displacement, here displacement is more, here displacement is less between point, it's a straight line. But if the force into displacement, that is work done, is same in both cases, and it is same in all possible paths I take from point A to B, then magnetic force or vector field is considered as path independent. If it is path independent, means it doesn't matter point A and point B are connected through a straight line or through a circular line or through a parabolic line, through a staircase, haphazard, any maze kind of thing, whatever it is. So it is only dependent upon point A and point B. In that fashion, if I take a full path, point A to point B and point B to point A back, then it should be 0. If that is also I prove for all possible paths. Now, if this is a straight line path from point A to point B and point B to back to point A, if it is 0, then this is considered as path independent one, because it depends upon, it doesn't depend upon the path, depends upon the end. Earlier end was A to B, now end is A to A. Either it goes from B back to A, whatever. End result is A to A. I want the work done. It should be 0. If it is not 0, if it is 0 for some path it is not 0, then vector field is not path independent. Or from A to B, if it is, for if it is straight line, circular line, whatever, if it is different for one case also, it is not same for all cases, then it is not path independent. Okay, how I can prove that vector field is path independent or not? One proof that we suggested, that what is the actual work done calculus fundamental. If I have a force vector, work done happens through vector, where force and displacement must be in the same direction, then only we can calculate the work done. If this is the force and displacement is happening in this direction, then force cos theta first I have to find, then force will reduce. Then I have to calculate the displacement, or force vector dot the displacement vector, r vector. Force vector dot r vector is the work done. If it is calculus, then force vector dot dr vector. Calculus in the sense that force vector is vector field. It is not a static vector that it is in one direction only. And depending upon its independent component x and y, the force vector will keep changing. Like r vector is not a straight line. Okay, it is also a vector field that will keep changing. Like circle. Circle is not a vector, right? It's not a numeric vector that it is one. If I take position vector of the circle, then it will go like this. If I had taken xi as magnetic force, then depending upon the x magnetic force, magnitude is increasing. If I had taken xi plus yj, depending upon the xy, the direction will also change. Xi direction will be same, but if it is xi plus yj direction. So these are vector field, capital F. So if both are static, capital F is static and displacement is static, if both are static, then F vector dot R vector, displacement vector, I can find the work done. But if both are vector field, then F vector, that is algebraic vector, dot d comes into the picture. It becomes calculus now. D R vector, capital F vector dot d R vector. Now this is the work done. Integration from point A to B. This is what we are trying to find. Now R vector is different. Capital F vector, that is a vector field that is same for all the paths, but R vector, sometime it is straight line, sometime R vector is circle, sometime it is parabola, sometime this is this, that, but capital F dot dr vector should be same for all R from point A to B. If that is the case, then vector field is considered as path independent. Okay, later we will merge into curl fundamental, but right now we are proving that vector field is path independent or not. Means whatever the work done, that is only dependent upon the vector field and beginning point and end point. If beginning point is A and end point is also A, irrespective of it has taken what path coming back to A, it should be 0. Or beginning point is A and end point is B, whatever path we think possible path between A and B, it should be same. Then vector field is path independent. Okay, the proof what we proposed is that R vector is different for different kind of path, but it is generic if I take it as xi plus yj. Because for every path, if I take any point, then it will be xi plus yj. So if that is the case, then dr vector becomes dxi plus yj, dx plus dy, dx plus dy. And here force vector capital F, I can now break it down into f1i plus f2j. Both will become, if I do dot product, it becomes f1 dx plus f2 dy, integration a to b. If that is the case, then f1 dx and f2 dy plus f2 dy will turn up, this integration will turn up into an algebraic equation. This, okay, f1 dx, if I integrate, it will turn up into algebraic equation, plus f2 dy, it will turn up into algebraic equation. Addition of two algebraic equation, and then setting limit from a to b. Whatever algebraic equation we are getting, that is also called small f potential function. So whatever potential, algebraic potential function we are getting after this, that is f1 dx, where f1 and f2 are component of vector field f, f equal to f1i plus f2j, everything in capital. So f1 dx plus f2 dy will result, the final integration will result in potential function small f, that is algebraic function. If that is the case, then if I want to recreate f1, if f1 dx plus f2 dy in capital, it becomes a small f, that is potential function. Then if I do partial derivative of this potential function along x and y, we also call it creating the gradient. So if I create the gradient of a small f, that is small f, df by dx I plus df by dy j, then it would be same as f1i plus f2j, or f1 dx plus f2 dy equal to small f, or small f df by dx should be f1 and small f df by dy should be f2. If this is the relationship, if we are getting this relationship, then this integral f1 f dot dr vector, it is not dependent upon the r, because whatever result we are getting small f because of this integration, if I calculate the gradient of this, then it is becoming f back. Getting right? So r vector, capital F vector dot dr vector. Dr vector is different for different kind of path from A to B. Consider it is a generic path, that is xi plus yj. Because if it is a circle, then also it is xi plus yj. If it is a line, then any point is xi plus yj. So this is xi plus yj. If I do f1i plus f2j dot d of xi plus yj, it will become f1 dx plus f2 dy. Integration will result into an algebraic equation, that is small f, that is potential function. If that is the case, then f1 dx plus f2 dy, this is simple integration. If this is simple integration, means it is not dependent upon any path. f1 dx plus f2 dy, there is no intelligence for any path. It is a straightforward integration of a vector field capital F. If that is the case, then I am getting a potential function of small f, that is only because of capital F, not because of the path, r path, because r path we have taken xi plus yj is a straightforward case. Then this potential function small f, what we are getting because of f1 dx plus f2 dy, this small f is only because of capital F. If that is the case, then if I calculate the gradient of a small f, then it will become f1 plus f1 and f2 again. I mean, if I have potential function small f, then df by dx become f1 and df by dy become f2. If that is the case, then it is path independent. What we are trying to get here? So many times we are repeating here and there. What I am trying to say, that if I find any potential function, any algebraic equation for which gradient is vector field f, then it is path independent. This is what we are trying to say. Because we proceeded from f dot dr in path independent fashion and we came to small f. So the way we came to small f looks like if I calculate gradient of a small f, it will result back in vector field. If that is the case and we had taken generic path, this proves that the gradient of any algebraic equation, if it results in vector field f, then it is path independent. Because we started a discussion with path, generic path only, means path independent. So if I start the story with xi plus yj as a path, as r vector, then we land up in a situation where the end result, that is the potential function of small f. If I calculate the gradient of a small f and it goes back in capital F, then this small f, the whatever we are getting, it is not dependent upon the r vector. If that is the case, then it is path independent. What is the result? Can I find an algebraic equation in the world where billions of algebraic equation is possible? Can I find an algebraic equation small f for which the gradient vector is vector field? If that is if it is possible, then we found the solution, that this is the way that I can test that it is path independent, because we started with the path independent xi plus yj as r vector, and slowly we came up with the way we come up to the potential function. It looks like the gradient of potential function is f vector completely, or small f df by dx, that is f1, and df by dy is f2, because f1 dx plus f2 dy is small f. If that is the case, then reverse is also true. So can you find a potential algebraic function small f for which the gradient is the vector field capital F? If you find, then it is path independent. Simple case. If it is path independent, then no need to go for the kind of line, it is called line integral, capital F dot dr vector. Okay, if this is the vector field and this is the path, I'm trying, if iron piece is moving from point A to B, how much is the work done? Then vector field F dot the line integral, full line, it will do the multiplication at each point, that is the calculus. Then if that is the case, then it is called line integral. So rather than calculating line integral, if consider r vector is very complex, r vector is very complex, like circle, where y equal to square root of a square minus x square, or parabola, or very complex. Then capital F dot dr vector, if you first settle it down, it will be very complex, and then integration is impossible. Then you have to go numerical way to find the integration point A to B. But if I know any algebraic equation for which gradient is the vector field, then it is path independent. If it is path independent, then in that algebraic equation, just if small f is the algebraic equation and we are trying to find from point A to B, just say fb minus fa, small fb, whatever the b point is, just set it into the algebraic equation potential function minus set a. Whatever you do, that is the line integral, that is the work done. It is also called potential energy in the gravitational pull. If this is the gravitational pull, it is going towards earth, and this is point A and this is point B. What is the work done when path is circular, not straight? Okay, I have a pipe. Inside that pipe, I put a stone, and the stone is moving like this. How much is work done by the gravitational pull on this stone? Then I have to do, this is the gravitational force and this is the line. So gravitational force into line integral, not required, because I know gravitational force is path independent. If it is path independent, then try to find one algebraic equation for which the gradient vector is this gravitational force. If that is true, then that algebraic equation, set b point, calculate the value, and set a point, calculate the value, just subtract it, that is the work done. That is nothing but what is potential energy here and what is potential energy here. If you subtract, that is the work done. So potential function is also termed as potential energy function in kind of in gravitational pull. So this is the proof from our side. We started from the generic path xi plus yj, and we came to a situation where if I have a if I have a gradient, if I have a potential function whose gradient vector is vector field, if I find such kind of potential function, then it is path independent. Let's try. I have equation force vector or vector field xi plus yj, xi plus yj. This is xi plus yj. This is x-axis. This is y-axis. This is xi plus yj. If x is, I mean, this is a vector field. So if y is 0, then this is the vector. If x is 0, this is the vector. Otherwise, it is like this. So this full arena, I believe 360-degree, full arena is the vector field. If that is the case, then if the circle is placed somewhere from point A to point B, point A to point B, what is the line integral? What is the work done in this vector field? If I find any algebraic equation for which the gradient is the vector field f, that is xi plus yj, then just set that small f, that is the potential for fb minus fa. That's it. That is the work done. Rather than calculating the full f dot dr, full the kind of concept and then integrating, not required, because I know that this vector field is path independent. So if it is path independent, then f1 dx plus f2 dy will result in a potential function f, small f, or gradient. If I have to, at the end I have to calculate the gradient function small f. So small f gradient function, if small f function, if I calculate gradient, then it should become vector field capital F, then it is path independent. So what is the algebraic function for which gradient vector is xi plus yj? That is x square by 2 plus y square by 2. If this is the algebraic function, let's calculate the gradient. So small f x comma y, that is function over x comma y, equal to x square by 2 plus y square by 2. Then df by dx, where small f is small, df by dx is x, so xi, and df by dy is y, then yj, same as vector field xi plus yj, right? This proves that I found one potential function whose gradient is vector field f. If that is the case, then I can go with our rule that our path is generic, that is xi plus yj. If that is the case, then f1 dx plus f2 dy will be x square by 2 plus y square by 2. Same, right? xi plus yj is the vector field, then x dx plus y dy is x square by 2 plus y square by 2. Indeed it is. Okay. If that is the case, then we prove that. Now how to find the from point A to B? Consider that this is x-axis and this is y-axis. Point A is 1, 0 and point B is 0, 2 on y-axis. So what is the work done from 1, 0 to 0, 2? Now someone will get the vector equation of line and then xi plus yj dot and then line, then full, not required. You know the result. Potential function, that is x square by 2 plus y square by 2 from one point to one point. Now set one point to another point. First the lower point is 1 comma 0 and higher point is 0 comma 2. So 0 comma 2 will become 4 by 4 by 2, 2. 2 minus 1 comma 0, that will become 1 by 2, 3 by 2. That's it. So simple, right? Rather than going with full line integral. But anyway, we are talking about curl. It is not that straightforward. Now consider the case that is x plus yi, x plus yi, x plus yi is the vector field. Can you find a potential function for which gradient is x plus yi? That is the question. Can you find a potential function for which gradient is x plus yi, x plus y in bracket I? Okay, let's start from our fundamental. So x plus yi dx plus 0 dy, because there it is 0. X plus yi x plus yi dx plus 0 dy. So this would result in x square by 2 plus yx. So fx is x square by 2 plus yx. If that is the case, then df by dy should be 0, because f has two components, x component, f1 component and f2 component. Small f. The small f, if I go with partial derivative along x-axis, it produces f1. If I go with partial derivative along y-axis, it gives me f2. So through f1, that is x plus y, I calculated small f, that is f1 dx, that is x square by 2 plus yx. Now the potential function small f is x square by 2 plus yx plus any function in y only, because if I differentiate with x, it should become x plus y only. So the small f is x square by 2 plus yx plus any function in y only. So that is df by dx would result in x plus y back, because other function in y will go away in df by dx. Consider that other function is cy, a function called cy. A function is c of over y. So the small f, that is potential function, is x square by 2 plus yx plus cy. If I do df by dx, it will result in x plus y I1. Okay. Now if I do df by dy, then it will result in x plus gradient of c function. X plus gradient of c function, that is equal to 0. What is cy? So gradient of cy equal to minus x, not possible. The gradient of cy is minus x, then integration of cy, that will result in cy, will be minus xy, but that should be function of y1. There should not be any x over there. If that is the case, if that is that, there only it got scrapped. If the derivative of cy or gradient of cy function is minus x, then cy will be minus x dy minus xy. But then cy has to be function of y only, but it has x also. So this proves that x plus yi, if it is a vector field, then there is no potential function exists in the world for which the gradient vector is x plus yi. Not possible through our fundamental. If that is the case, then this vector field is not path independent. We will try another proof also. Then we will try another proof also. So curling is the most considered as the most difficult in calculus. So it will take time to adjust. We are repeating many things again and again so that it will hit the brain. So that we will see.